There we go. All right. Great. So next up we have Noah, who's going to be telling us about programming by demonstration for long horizon robot tasks.
All right, hi. Yeah, I'm Noah, so I'll be presenting, as was told, my paper titled Programming by Demonstration for Long Horizon Robot Tasks. The main contribution of this paper is a novel algorithm for synthesizing programmatic robotic policies from demonstrations. So you might be wondering, what are programmatic robot policies? Well, programmatic robot policies is essentially a program that's specifically designed to govern the behaviors of a robot. But why use programmatic policies rather than neural network policies, which have been responsible for much of the recent progress in robotics? Well, the answer is they don't generalize very well to different environments. They are difficult to interpret and verify, and they have a lot of data which is required to train. On the other hand, programmatic policies are generalizable to multiple environments, are interpretable and amenable to formal verification, and can be synthesized effectively from less data. And so now that I've motivated the utility of programs for robotic tasks, I'll discuss some of the properties that these programs must have. These programs must enable long horizon tasks, for example, household chores or restaurant work. Moreover, these tasks often have repetitive steps, which necessitates complex loop structures in the program. And additionally, these programs must enable decision making, which requires conditional blocks. Lastly, these programs must be able to execute in large environments with many object types, locations, properties, and relationships. And both of these factors end up yielding a very large program space. I'll now give a representative example program to demonstrate the complexities of programming with robot policies. Here's a program for a robot that must visit all of the rooms in a hotel and collect the dirty bed sheets. This requires going to each room, finding a laundry bin in the room and opening it, finding all of the bed sheets and beds in the room, then checking if any of these sheets are dirty and on the bed, and if they are, grabbing them and putting them in the bin. Lastly, before leaving, the robot must close the bin. Notice that this program has multiple nested loops, perception of appropriate objects, and conditional flow based on these perception results. And writing such a program requires expertise, resources, which makes it difficult for end users of a robot. This motivates the use of programming by demonstration, wherein programming by demonstration requires an end user to provide just a demonstration for the task at hand. This demonstration is then passed through a synthesizer, which generates the final program. And providing such a demonstration is much easier than writing a program for end users. I'll now explain how a demonstration for the program we saw earlier can be easily generated by such an end user. A demonstration consists of a sequence of actions over locations and object instances. Each demonstration takes place in a specific environment with specific locations and objects. For example, let's assume the hotel has 2 rooms, each with beds, sheets, and laundry bins. In this environment, the user provides a demonstration for the task at hand as follows. First, they go to the room and open the bin. Then they go to the first bed with the sheet and take the sheet and put it in the bin. Then they close the bin before going to the next room. Similarly, in the next room, they go to the bin and open it. They go to both beds and grab both of the sheets and put them in the bin and close it before leaving. So now with the utility of programming by demonstration motivated for robotic tasks, I will move on to explaining our approach. In this paper, we present a novel algorithm for programming by demonstration, specifically designed for such long horizon robot tasks, namely PROLEX. Our approach in PROLEX begins by generating a program sketches from the given demonstrations, using a novel reduction to learning regular expressions from positive strings. Next, we perform a top-down enumerative search over our DSL to generate a set of candidate programs. A major novelty of our algorithm is a refinement technique where a large language model is used to guide the process of partial program completion. Lastly, our pruning method uses a novel technique for abstracting partial programs into regular expressions, which is used to prune away unrealizable partial programs earlier in the search. I'll now break down the components of PROLEX and start by discussing our sketch inference engine. We made the observation that this could be reduced to a problem of learning regular expressions from positive string samples. This learning problem is very well studied in the literature and has many off-the-shelf implementations. The steps of our inference are as follows. Given demonstrations, we abstract the sequence of actions into a specific string form. We then use an off-the-shelf regex learner to generate a regular expression that accepts these strings. And finally, we translate the learned regex into a program sketch. The first step of sketch inference is a demonstration abstraction, which simply replaces the object instances in the demonstration with more general object types. This is important for later stages of our synthesis, for recognizing repetitive patterns in the demonstration. After generating the abstract string, the next step in our sketch inference is to learn a regular expression that accepts the string. Such a regular expression essentially generalizes the abstract string into a structure that captures conditional and repetitive patterns in the demonstration. For example, when using an off-the-shelf learner, this is the expression that was learned from the given demonstration above. As you can see, the pattern in the demonstration is captured by the regex. In both rooms, a goto is followed by a bin opening, which is also followed by a group of actions responsible for picking up and placing sheets. And lastly, the bin is closed before leaving the room. All of this is picked up in the regular expression that's learned. And now that we have a regular expression that generalizes the given demonstration, we can easily translate this into a program sketch. Specifically, all of the Kleene stars represent loops in the program, including the nested ones. And the conditional sub-expression, denoted by the question mark, represents a conditional block in the program sketch. These translation rules, when applied to this regex, produce the following sketch, with the nested loops from the Kleene stars and the condition. And now that we have a sketch, I will describe the next step in PROLEX's algorithm, which is to find completions to these program sketches. As mentioned, our algorithm performs an enumerative search over a DSL. Completions for unknown holes in the sketch, performs an enumerative search over a DSL to find the completions in the sketch. However, as you would expect, naive enumeration becomes quickly intractable. To address this challenge, we come up with a novel idea to use a large language model to guide and prioritize our search for sketch completion. Specifically, we observe that large language models work well as common sense priors. In this work, all of the hole completions have real-world semantics, which can be reasoned about by large language models. I will now walk through an example and show how a large language model can be used to prioritize the search for sketch completions. Here is a partial version of the program we saw before. There are multiple holes in which our synthesizer must find appropriate completions for. Here's a list of the completions for the hole shown. As you can see, the correct object sheet is one of the candidate completions. However, there are many potential other completions that might appear in the list before, which the synthesizer must enumerate before checking sheet. Looking elsewhere in the program, though, we can see that this hole fill corresponds to an object which must be on top of a bed. With this knowledge, we can now reorder the list of candidate completions such that objects may be found on top of a bed will have higher priority. Similarly, with the dirty predicate, we can again reorder the list and deprioritize other options which are less likely to be relevant in this context. This type of reasoning is well suited for large language models and allows our synthesizer to reorder completions for each hole and guide the search toward the target program more effectively. In summary, PROLEX uses large language models as common sense priors over the real-world semantics, with the partial program as context to guide enumeration towards more likely partial programs based on the language model's score. However, even with the gains made by the large language model sketch refinement, many non-feasible partial programs must be elaborated. This motivates our pruning procedure. Our pruning strategy uses a form of abstract interpretation where, similar to the idea of treating demonstrations as strings and learning regular expressions that can be translated into program sketches, we also observe that we can over-approximate a partial program as a regular expression. The idea is to infer a regex such that if it does not accept the string representation of the demonstration, we can soundly prune away this partial program during our search for the target program. In our paper, we introduce a novel algorithm that, given a partial program, infers an over-approximating regular expression to be used in the pruning procedure. At a high level, we first use partial evaluation to generate a string of the known statements that will be produced by the execution of the partial program. This is to maximize the known information in the over-approximate regex. Then, to transform the remainder of the partial program, we must determine the potential number of loop iterations and the set of potential condition block evaluations. The idea is that the more partial programs, we can eliminate more partial programs, the more specific our over-approximate regex is. You can find the details of this algorithm in our paper, but I will walk through now an example showing how certain loops in the program can be over-approximated using knowledge from the demonstration environment. Here we are given a loop with a hole to be completed. We know from our DSL that this loop occurs over an object type, and based on the information in the environment, could be filled with 2 cups or 3 forks. We generate an over-approximate regex of this code fragment based on the set of potential loop iterations inferred from the environment. In this case, we have the disjunction of the loop repeated 2 or 3 times. This regex is much more informative than the loop that is repeated an unknown number of times, which leads to more pruned partial programs. Additionally, we prove in our work that the partial programs pruned by this methodology will not yield programs that are compatible with the target program, or with the demonstrations. Thus, our method will not miss compatible complete programs where they exist. I will end the talk today by going over some of the results from our evaluation. We evaluate on a benchmark of 40 tasks derived from a robotics benchmark named behavior. We evaluate on 3 varying environments, which are easy, medium, and hard, based on the size of the environment. The environments have over 1,000 object instances and 80 object types, which all of this leads to a potential program space of over 4 million complete programs per task. PROLEX, with this in mind, was able to find a program consistent with the demonstration for 80% of these benchmark tasks, with a 2-minute timeout and 1 demonstration. Moreover, PROLEX was able to find the ground truth program for 81% of these tasks. We also found that with more difficult environments, our solution was able to find more programs matching the ground truth program. This is because the more challenging environments allow us to prune more candidate partial programs. We also compared to the Cygus Solver CVC5 as a sketch completion engine. This was done by defining our DSL over using syntactic constraints and generating semantic constraints based off the initial and final world states generated by the demonstration. We found that CVC5 could not adequately find programs without first being given a sketch. And even with that, we found that on easy environments, CVC5 could only find consistent programs on 25% of tasks within the time limit. Lastly, we used GPT-3.5 as a baseline solution for this problem. We found that comparing GPT-3.5 by giving a specification of our DSL, the full environment, and the demonstration proved difficult, as when given only a fragment of the environment, GPT-3.5 was unable to solve any of the tasks. To reduce the amount of information given to GPT-3.5, we omitted the information about the environment and asked it to produce the final program. Here, it was only able to find consistent programs 45% of the time, and was only able to find a program matching the ground truth 25% of the time. To summarize, PROLEX implements a regex-based sketch inference method using an off-the-shelf regex learner. PROLEX utilizes large language models as a common sense prior to complete holes for the sketch. And PROLEX provides a novel over-approximated regex pruning strategy and is more effective in realistic, long-horizon tasks than baselines. Thank you.
Great, we have some time for questions. Any questions from the audience? In the back.
So these look like high-level plans for a robot rather than, movement or other things.
Yep.
How realistic are these programs in the sense that can you actually run a robot with just this amount of instruction?
Yeah, so that's a good question, actually. So some of what I'm working on right now is getting these programs to actually evaluate on real robots. So I'm co-advised with a roboticist professor as well. So right now, one of the difficulties we have is with actuation with arms. So picking things up is still a challenging task for robotics. So we're focusing on an information gathering task right now with similar programs where we would go around and collect information about environments. And so we're working on a method to do that. So it is pretty realistic.
And you could drop a sheet, and there can be humans in the room, and there can be so many things.
Humans in the room is fine. the actuation stuff is a bit difficult for like picking things up. That's still like a pretty open problem in robotics generally, but yeah.
Question here. Oh, and maybe the closer one. I don't know who was first. Maybe he was first, I think. So why don't we let him ask first? Yeah, sorry.
I was just wondering if type information could be used to, for instance, specifying that bins should only contain sheets.
Yeah,
so
yeah.
That you get some. Yeah.
That is actually part of our solution. I didn't get into that too much, but we have like a lightweight type system. So, for example, properties. If we're inferring, where is it? I don't have to show it, but in some cases, like properties can be covered by a set of objects. So we know that certain properties don't have certain objects don't have certain properties, like they're not applicable. So that's also part of the way we refine it a little bit. But I was focusing more on the large language model guided refinement.
Now in the back there, yeah.
Thanks for the nice talk. So I have two questions. One is, do you care about the interpretability of the regex? You showed an example where you have source code and regex side by side. And I'm wondering if the regex corresponds to natural programs that a human would write. The second question is, if you have multiple holes, how do you prompt the LLM to synthesize? Do you search for the combination of all the things that would fit in all the holes, or thanks?
Okay, yeah. So I'll answer the second question first. You might have to repeat the first question. For the second question, we just do one hole at a time in program order. We experimented a little bit with doing a couple different like orderings of holes, but we didn't really find much of a difference with that. So basically what we do is we give all the context up until the first program hole, and then ask it to solve or find a completion for that hole, and then move on in the partial program search, essentially. And if you could repeat the first question, sorry, I'm not sure I quite picked it up.
Just curious about the interpretability of the synthesized regular expressions.
Yeah, so I guess when I was talking earlier about interpretability, it was more so about the program itself that gets implemented. I think some of the regex we find aren't super interpretable at first glance, but going through like the sketch translation rules we have, the programs that get generated are pretty interpretable, I would say. I don't know if that answers your question. Okay.
We have a question here.
So in your experiment, have you investigated like out of distribution generalization? So demonstration is with respect to say length, like 5 rooms. You want to apply, see whether the program you learned can be applied to a hotel with like 100 rooms and so on, and see what happens.
Yeah. So the way we did like our interpreted generalizability is once the program was generated, we like did an eye test, like manually inspected it and see if it matched the ground truth program that we were expecting. And then based on that, we know that whether or not it would generalize to more programs, because the ground truth programs will have like loops over all of the rooms, for example. So in a hotel with 4 rooms or a hotel with 100 rooms, it would have the loop would repeat that many times based on that. So yeah, we didn't really experiment with it, but.
Thanks for the talk. I was wondering, it's a very naive question on my part, but I was wondering whether regular expressions were actually expressive enough to capture like a lot of the programs you would want to have. Mm-hmm. For example, if you want to, for example, regular expressions can't do things like, like having, checking if a string has like a same number of like A's and B's, for example. Then like we can imagine a program for a robot whereby you would want to like say pick up all the folks, no matter how many they are, and then like put all those folks in a place, for example, and that would enable that would essentially be of a pattern of like A to the n and B to the n for any n. And I was wondering like whether you had whether this whether you had considered this and like whether this is actually like an expressive enough representation?
Yeah, so we found that the regex are expressive enough for our DSL, and then the way that we've implemented the sketch translation rules. So that example that you gave would end up referring to like 2 sequential loops, essentially. So there would be a loop going through, we'll save one room for simplicity, but going through all the room, finding all of the forks and picking them up, and then a second loop of placing all of those forks in some specific location. So it'd be able to pick that up from the demonstration. You would have like a block of picking up, like basically what the demonstration for that would look like would be like a block of picking up all of the forks, and then a block of picking up all of the, or putting down all of the forks in some place. And then the regex you would get for that would be like a cleany star over that first block, and then a cleany star over that second block. Does that answer your question?
All right. Well, let's thank our speaker very much.